Before we get into the main topic, let me introduce myself. I'm Nelson Correa. I'm a data scientist and machine learning consultant focused on NLP. I have a PhD degree in electrical engineering from Syracuse University, where I actually did my dissertation on symbolic NLP back in the late 1980s. I worked on syntactic analysis of English. I have worked at IBM Research on NLP and machine translation, and two startups in New York in the field of language instruction and speech recognition. I'm currently with Bank of America, Chief Data Science Office, or CDSO. And I like to say that nothing in this presentation is work done at Bank of America or approaches or opinions of Bank of America. So let's go briefly over the goals of this talk. So we're going to be covering the state of the art in NLP, which is the use of, with the use of neural networks that have replaced symbolic and statistical approaches of the past. And NLP is the hottest area of AI. So, this talk is broadly about AI as well. What are the pros of the new neural approaches to NLP? The main ones are the human and superhuman levels of performance that can be achieved with these methods on the data sets and benchmarks established to measure that. This is due in large measure due to the end-to-end training that can be done with these neural networks. And the performance obtained by these NLP models now have opened them wide, for new consumer products and applications, and for use in the enterprise, generating a big interest in the field. And what are the drawbacks of these models that we'll discuss? The main one is the size to which these models have grown. Now we talk this year of models with over 100 billion parameters, raising issues in the amount of training data that is required to train those models, and the computing and cost. And also, interestingly, as we'll see after I present the models, it turns out that similar performance can be obtained with much smaller models of the order of 0.1% of the size of the most recent ones. Also, very importantly, these large models, large black box models, raise questions in the ethics of AI and related topics: bias, privacy, fairness, risk, transparency, and accountability, all of which require some degree of model interpretability and prediction explainability. They also raise questions about what is being learned and how. So questions of data modeling, data governance, and model risk management. We conclude the talk with a note of a new approach, a hybrid neuro-symbolic approach to AI and NLP that is coming out. We have 5 main topics in this talk. So I'll start with the basics, defining a language in terms of words, symbols, sequences, and vector spaces now. Then we discuss the NLP pipeline that applies both in the symbolic and neural methods. Then we discuss language models, which is a central topic in language understanding. Neural NLP, where the focus of the presentation is, and we conclude with the presentation of the new Neuro-Symbolic Systems. So let's start by defining a language, which in turns is based on a vocabulary, which is a finite set of words or tokens or symbols or forms. In a language, in a language application, we have vocabularies that can be anywhere from the tens of thousands of words to millions of word forms, depending on how much inflection and compounding is in that language and what kinds of normalization are done on the text and the vocabulary. But importantly, this vocabulary is a discrete collection. It's a discrete set of symbols that can be represented by a label, an integer, or a one-hot binary vector. A language is a set of sentences or documents, and each of those is in turn is a sequence of words. N-grams, or short collections of contiguous words, let's say 3 words at a time, are used to model language, especially statistically. And once we start looking at these combinations of words, for example, in N-grams, we come up with the complexity of language. So if we have a vocabulary of, for example, 100,000 words, and we wish to consider trigrams, n equal 3, then we will have 10 to the 15 possible trigrams. So that's, of course, an astronomical number, more than any corpus can be in size. So in any corpus, most of the trigrams won't occur at all. And that gives rise to the problems of estimating these models. A recent trend of the last 20 years, but especially the last 5, is that the modeling of language and vocabulary has gone from discrete representations or discrete symbols to continuous vector spaces, dense continuous vector spaces, where words are represented in a lower dimensional space than the size of the vocabulary. And we will see that coming up. I like to show an illustration of this vector space representation. So this goes back to the work on information retrieval. Back then, in the 70s, documents could be represented by Boolean matrices of occurrence of words in documents, as shown on the top in the Boolean model, or in the smart information retrieval system. A continuous representation was done in terms of word frequencies in the documents, or normalized word frequencies, for example, in the term frequency, inverse document frequency, or TF-IDF method was done. And then the dense representations, which are more recent, use, as I said, representation in a lower dimensional space, let's say dimension D, much smaller than vocabulary, and models such as word2vec or GLOV or global vectors can have dimensions of size, let's say 300. Importantly, these dense semantic representations enable definition of similarity measures between words and documents in that vector space. Let's move on to the NLP pipeline by starting with the base NLP tasks in any application, in any analysis. So given a document, the basic tasks we need to consider are tokenization of that text, tagging, for example, with part of speech or senses of the words, etc. Chunking of the text into smaller units, for example, proper names, name entities, and parsing of that text, especially in the symbolic approach. And with these base tasks, all kinds of applications can be built. For example, in search, text classification, information extraction, text generation, transcription, and so forth. These tasks are organized in the so-called NLP pipeline that can now be assembled very simply with any of the machine learning toolkits supporting text. For example, scikit-learn has good facilities for that. And then there are specialized toolkits such as Core NLP, NLTK, spacing, and so forth. At this point, we can start to draw the differences between symbolic and neural NLP. In symbolic NLP, higher levels of analysis are done, especially parsing, computing logical forms of sentences and documents, and semantic representations of language and discourse and so forth. With neural methods, the approach diverges right there after the base NLP pipeline, in that the common approach is to compute a fixed length vector representation of any of the entities of interest, words, sentences, documents, and so forth. And then those representations can be used to perform the task at hand. For example, text classification or decoding that representation into a sequence, as in sequence-to-sequence applications. For example, machine translation or speech recognition. This approach in neural NLP have led some to note the end of parsing or possible end of parsing with the neural methods. Here we have an example NLP pipeline. This is from the SPACY language toolkit. And such a pipeline can be set up with just a few lines of code as shown on the left from their documentation. Let's say a few more words about symbolic NLP and sentence parsing and logical form, so we can contrast the approaches here. So symbolic NLP and a lot of modern linguistic theory was done by Noam Chomsky, or started by him in the 1955 to 2000 period, roughly. Started with the work on formal languages, which are also used to define programming languages and compilers. The main assumption here is that generative grammar is a description of the human language faculty. A key ingredient of this is the compositionality of representations and the notion of acceptability of a sentence, which is a binary concept. A sentence is or is not in the language. And we have an example sentence here, short one: who did John seem to love? So we have two verbs, seem and love, a noun, John, and so on. We have on the right a parse tree for this sentence. This is with one of Chomsky's theories, and this is actually from my dissertation in late 1980s. Also done in the 50s. So language can also be viewed not in terms of grammars, but in terms of corpora, which is a sample or a collection of text from a given language. And with such a corpora, it becomes possible to define the probability of a word or a sentence in the corpus of the paper. And with a vocabulary of 20,000 words, the entropy, looking at trigrams, 3 words at a time, is 6.8 bits per word. Perplexity, 109. So that's on average 109 possible words to continue a sentence. And this is from a well-known textbook in the field from Jurafsky and Martin. Let's move now to neural language models, which build on the previous one, the statistical ones, which are still symbolic models because they're looking at vocabulary as a discrete collection. So in 2003, there is one of the first works on neural language models by Joshua Benjo at the University of Montreal. He looked at the possibility of defining these language models with a neural network, in this case, a simple one, a multi-layer perceptron with a single layer, and taking 3 key ideas for this. The first is that the words would not be represented discretely, but instead as dense, continuous word feature vectors in a low-dimensional vector space, Rm, where m is 100 in this case. The second is that the joint probability function of the model is going to be computed in terms of those feature vectors rather than the words themselves. And the third idea is to estimate the word feature vectors and the probability function jointly as part of the training data. This training was done on the Brown corpus of about 1 million words, and the Associated Press News corpus. So the model proposed here is the multi-layer perceptron on the right. So at the bottom, we have the input words, 3 at a time with the indices. Those are converted to 100-dimensional dense vectors. Then we have a hidden layer of the perceptron. And then we have an output softmax on that hidden layer with 1 output per word in the vocabulary. So that's about 10, 20,000 dimension for the softmax. Since this model was proposed, which achieved some improvement in the perplexity and entropy obtained from this language model compared to the hidden Markov ones, although it wasn't a huge improvement, but it was an improvement. Since that time, more elaborate models, neural models have come using recurrence, such as with RNNs and LSTMs, and new models with a new concept called attention. So in attention, the idea is not to look at just a small context, an n-gram context for estimating the probabilities, but instead to look at the full input sentence. So, but focusing on certain keywords at the time for whatever the task is at hand. In this case, it's predicting the next word. So this model was proposed also in Benji's group back in 2015, and is shown here. This idea of attention was taken up in 2017 at Google, where the transformer was developed with attention as a key element. So the transformer is an encoder decoder architecture. We have an encoder on the left that takes an input text and computes an encoded representation, fixed length of that input text based on the whole input. And that encoding can be used in the decoder on the right, which also takes as one of the inputs at the bottom, the past outputs of that model to produce output probabilities for the next word in the sequence, if you use it for language model or perhaps for other tasks. This model is quite large, given the architecture. Those models encoder and decoder that base transformer and say, you know, this is useful not just for sequence to sequence machine translation, but the encoder portion can be a general purpose encoding method for documents. So they created BERT, which is a universal encoder using two tasks, mask language model and next sentence prediction. The model can be pre-trained on a large corpus and fine-tuned for particular tasks of interest. For example, question answering, name entity recognition, natural language inference, and so on. The BERT large model has 340 parameters at this point. OpenAI, the outfit set by Elon Musk and others at Palo Alto, took the transformer and focused instead on the decoder portion of it, with the main goal of doing language modeling, predict the next word. And using that architecture to perform interesting tasks by allowing, for example, to input a language prompt using the same architecture as GPT and GPT-2, 275 billion parameters, you know, with the number of layers, dimensions, number of heads, and so forth. The model is trained on with 175 billion parameters, now has enough memory to store the entire training corpus on it. In fact, to store Wikipedia, English at least 300 times over. The compute time of this model, compute cost, is 10 to the 23 flops. So if we were to have as reference training on a single GPU, V100, given the performance it has, that would take 355 years. And given the cost of those GPUs per day or per hour, training GPT-3 would cost anywhere from $4.5 to $10 million to train. And a question we have to ask is whether this size is justified. And by the results in the GPT-2 paper, GPT-3 as well, the answer is yes, because as model size increases, the performance increases. But very recent work, including from this month, show that with alternate models, different architectures, or with model distillation of the large models, the same levels of accuracy can be obtained with 3%, 1%, and even 0.1%, as for example, in the work of Schick and Schütze cited here. These large models also raise questions of data modeling and governance. I submit these models are conflating at least three types of knowledge. So knowledge of language, which is the main goal of a language model, world knowledge, which is beyond language, basically relations and attributes of entities and relations used in language. And also just plain data facts, for example, what's stated in Wikipedia. All of those conflated into a single black box representation, and it's black box because we largely don't know how the representations are stored there. So this definitely raises questions of provenance, consistency, completeness, bias, and so forth in the data. The chart on the right summarizes the evolution of these models from about 2016 to today. Let's say starting with ELMO with 94 million parameters. We have BERT large at 340 million, GPT-2 at 1.5 billion, and GPT-3 at 355 million. And like I said, the performance of these large models can be achieved with models about 1,000th of the size. Let's talk as our last topic, the Neuro-Symbolic Systems and ideas for this. So this is a long-standing debate, you know, since the 60s and 70s. And the idea here is to take the advantages of both the symbolic methods, which have very rich knowledge about the domain, in this case, language and understanding, but that have as drawbacks that they are brittle, you know, because they're based essentially on discrete representations, and also because they have to be built mostly by hand, which is not very practical. And the advantages of the neural methods, which allow end-to-end training and have these continuous dense representations that have a number of very good features. So in a neuro-symbolic system, we want to take these opportunities into account for data representation, for example, the continuous vector representations, the trainable nature of neural networks, but at the same time bring in the inductive biases and that can be put into the architecture of the models from the brain, from perception, from memory, from cognitive faculties like language, from the levels of representation from these faculties and so on. And you know, we could talk of these physical symbol systems extended perhaps with these new notions of with the kind of architecture that can be obtained by combining the two approaches. Here is one example of a very recent system from this year, and this is from the MIT IBM Watson debater that is a descendant of the original IBM Watson Jeopardy program from 2011, which was a symbolic statistical system, not a neural system. So this Watson debater has some of these elements of a neuro-symbolic architecture. So it does have neural trainability, but it has an architecture with clearly defined points and tasks in between the input and the output. So for example, they're accepting a collection of arguments or statements about a debate. The arguments can be classified, polarity can be determined, illustrated some of the complementary strengths and weaknesses that they have, and address the hybrid model of a neuro-symbolic system. We touched on model risk of these models that stem both from the data, incomplete, inconsistent, irrelevant, malicious data, so forth, and from the model in terms of interpretability and explainability. As these models take high-level cognitive tasks that can be performed and automated, many implications come for society in terms of the future of work, model misuse, safety, ethics, and so forth. And in fact, all the major institutions are already looking at this both in academia and in industry. A couple of interesting podcasts are here from Stanford Human AI Institute. They're in the references. And we have an opportunity for advancing the state of the art in NLP with the neuro-symbolic approaches. Thank you for your attention, your present, and I provide here my contact information, and slides of this talk will be posted on my GitHub repository. Thank you again.